Okay, perfect. Okay, I am not seeing any first-timers who care to identify themselves. So we'll move on from there. So I have the great pleasure of introducing Dr. Julia Kamenetzky. Thank you. I listened to her give this, or a brief version of this talk in AstroTap. Was it earlier this year or last year? I think it might have been earlier this year. And it was excellent. So at that time, I asked if she would do us the honor of giving us the same talk. So with that, I'd like to ask you to come up and introduce yourself and start the talk.
Sure. Sounds good. I might put the presenter here.
Thank you. There you go.
Okay, awesome. Thank you. It moves. Awesome. Alrighty, so as mentioned, my name is Dr. Julia Kamenetzky. I'm an associate professor of physics at Westminster University. I think there's audio playing out of here. Can I mute yours? I'm hearing an echo from myself, maybe from the Zoom.
No, it's actually not. I think this is just the echo in the hall.
Okay, that works. Okay, cool. Yeah, and so as mentioned, I'm at Westminster University, and I am an astronomer, and you really don't have to be a professional astronomer to have seen beautiful images like this of the cosmos. Almost certainly the reason why you're in this audience is because at some point you saw these beautiful kinds of images and said, I want to know more about that, right? That captures our imagination. I did give a shorter version of this at Astronomy on Tap. So if you were there, I use some of the same jokes, but I do have more time to talk this time. So we'll also go into a little more detail about some of the things that we had to gloss over. In particular, look in more detail at this, one of these images in particular. So why talk about art when we are often here to talk about the science of astronomy? At Westminster, we have an honors college, and there's a student publication by the honors college published twice a year. And in the most recent version of the magazine, the cover story was called Art Makes the Mind, and it was about the art classes that are part of the honors curriculum that all students can take. So you can imagine a science student in an art class feeling a little out of their element, right? But also wondering, like, what does this have to do with my education? Why is art important? There was a quote from there that I wanted to share. The confinement of art as an activity of childhood, and only childhood, treats the discipline as meaningless play, positioning play as antithetical to serious inquiry. Instead, play is a way to interact with the world. There is always knowledge, experience, and learning to be gained from it. And I really enjoyed this because as a scientist, it's easy to, downplay the artistic and creative side of what we do. But I think it's very important because it is a way to interact with, in astronomy's case, the cosmos, right, that we're a part of. And so I want to think about how we represent hard data, facts and numbers in an artistic way as a form of play. So we're going to kind of play today with how we make images. That's the goal. So let's start by looking at a well-known star cluster from an astronomer's point of view. There it is. Yeah, it's breathtakingly beautiful, as I'm sure you're all feeling right now in your hearts. But for real, when I think about images, and particularly digital images that we might get from something like the James Webb Space Telescope, the Hubble Space Telescope, they are numbers. And so by arrays, I mean we have rows and columns, right? And each of these numbers represents a place in a picture, left or right, up or down. And so the number itself represents brightness. A larger number is brighter, a smaller number is darker. Okay, so you've got pixels, blah, but we don't like things looking like that. We want a lot of pixels, right? And so when you have a lot of pixels, then you can make an image that looks more interesting and detailed, right? So to understand exactly how we get the art out of all the numbers, first, you already saw the Wicked Witch of the West, but the reason why this is here is because we kind of need to do a reverse Wizard of Oz, and let's put ourselves into a black and white world, okay? So we're stepping out of the color world and imagine things only in black and white, then we'll better be able to understand color. But for now, just black and white. And something I also wanted to show you is that the tool that I'm using, that I take a bunch of these screenshots from, is called JS9-4L. Kind of a weird name. But if you were to search that exact thing, this would be the first thing that pops up. And it is a nice tool that shows all the things you can do with astronomical images that's very easy to use. So plenty of folks in this room that do a lot of image processing probably use a more complex, complicated software, or professional astronomers are going to use other things, but this has a lot of it, and it's really accessible for you to use if you've never done this before. Like, there are archived images. You can just take real NASA images, like with one click. There's video tutorials. You can even request new images from the NASA Micro Observatory. So there's a lot of cool stuff there if you're interested and you've never done this before, that you can play along with. All right. So if we're thinking in the black and white world, before we look at astronomy, because it'd be sad to look at beautiful astronomy pictures in only black and white, I have a different model for you that is a great black and white model, and that's my dog Sarge, because he's black and white. But in this black and white picture, you can't tell that he's sitting on a green blanket, but the rest of the details of him, I'm telling you, are pretty true to what you have. So what this is really an image. It's a grid of different pixels. You can't really see each individual pixel because it's taken with a high enough resolution camera on my phone. But suffice to say, what we have are different pixels. There's one I chose on his back. I clicked on that one and said, what is the number associated with that pixel? It's 228. And then I picked one on his head that's black, 17. So his back that has a lot of white fur is reflecting a lot of the light from the room, and so it's very bright. And black fur is absorbing a lot of the light, so it's very dark. In images like these, and often the ones on your phone, the numbers are going to go from 0 to 255 usually. That way you have 256 total numbers to work with, and computers love powers of 2, which that is. So if you want to present this as an image, what you do is you make a color scale, everything from black to white, because we live in the grayscale world, we don't have any color yet. Assign that a pixel with a 0 value is going to be there, very black. 256, 255, whatever is going to be white. And everything in between is going to be spread out in grayscale. So 128 is in between. And so every pixel gets a shade of gray that is associated with its number. That's the basic of a black and white image. But where we can go and have fun with it and play with it is change that color scale or things about it. So we're not changing the numbers in the image that say how bright or dark things are. That's where we might do our science, but we can change how it looks. So in JS9-4L, there's a thing on the right that says controls, and the first one says low brightness limit. If I change that, I can change that end from 0 to 40. Anything 0 to 40 now is the exact same shade of black. Can't tell the difference, and we're going to spread out the things from 40 to 256. So I don't know if you could tell the picture how that changes. High brightness limit kind of changes it on the other end then. There's something called stretch contrast, and if you, again, look back from one to the other, what I've done is change where the transition from black to white happens. I've kind of squished that to be more just only on the in-between numbers. And that makes things look really weird. So this is getting to the point where if I don't have Instagram, but I know there's filters on that, but I know like on my phone, if I look at a picture, it might suggest to me different filters that will make my picture look better or weird or artistic in some way. This is all some kind of variation on changing the color scales and how they look. And that's how you can get these kind of weird filtered looks. But these are the numbers behind it. And then the other one here is the shift bias. And what that's going to do is change that part that I have circled in red where we change from black to white. You could move that left or right. That's what we mean by shift. So I want you to think for a moment in your head. I'm going to move that black to white transition over to the right-hand side. Not in the middle, over to the right. And I want you to think, what are we going to see better in more detail? The details of his head and his face or his back, the spots on his back? Think which you think it's going to be. I'm going to move it to the right. I heard both face and back. We could do a little vote. Okay, who votes face? We're going to see the details of the face more. Who votes see the back? Who is like, I have no clue, I don't know, I just like dogs, or maybe you don't like dogs, that's fine. Okay, let's check it out. I moved it to the right. We see the back details a little more, the spots on the back. Here, I couldn't even tell you that there were spots there, right? I could, because he's my dog, I know. Here you can see that, come on, detail more. So how we change our color scale is going to change what parts of an image we can see the details of. And in this particular case, it's like the bright part or the dark part. And in the case of astronomical images, when we say bright versus dark, you might have an image that has features that are 100 times brighter than other features in the image, 1,000 times, 1,000,000 times. When we talk about astronomy and the scale of the cosmos, we can have huge ranges. And so this kind of shifting and bending of our color scale becomes really important in ways that we'll see. Okay, and then I think for good measure, I show you, what if we change it the other way? Then we can see, oh, look at every single gray hair he's gotten now that he's older, like, right? This is where we can see some of the details of the dimmer parts. Okay. If we go back to the normal picture, the other thing we could do is change not just like what the color scale looks like, but how we distribute the numbers within the color scale. So this is a linear scale because it just goes up. Every time you go up by a number of 10, you go the same amount to the right on the color scale. I could change that using a different scale. This one is called a logarithmic scale. And you can see that what I did was I really squished all the high numbers on one end, and the low numbers are kind of spread out, is what happens mathematically when you do that. That doesn't look great for a picture of a dog, but that really helps in astronomy with pictures that are, again, with this varied scale of brightness. A lot of the pictures you're going to see are actually a logarithmic scale. Now, you can also just go really wild and assign maybe colors to numbers that make no sense, right? And so this is a possibility. You can do anything you want with the numbers, right? And so you can get these weird, funky images that look like this. Something like this is what's called false color. So we're going to show you a lot of ways to play with how we represent bright and dark color with astronomical images, but they're not necessarily false color in the way that this assigns colors in ways that have nothing to do physically with the numbers. So keep that in mind. Won't be false color what we're showing you. Okay. All right, before we move on, if we want to talk about color, now we'll do the forward Wizard of Oz thing, but I don't have another animation for that. I had to think about what's a good way to represent color again on Earth that we know, and like we're not dealing with the big scales of the cosmos. And I'm a millennial. I was born in 1986, so my obvious go-to for color is Rainbow Bright and the Color Kids. I showed this to my college students, and they insisted to me that this was Sailor Moon. And I was like, listen, I don't have a PhD in cartoons, but I know the difference between Rainbow Bright and Sailor Moon. You get it, yeah. So this is Rainbow Bright. Anyway, let's talk about, again, when we look at colorful things in our everyday lives on Earth, what do we do with our eyes? And this is kind of a lesson that you might remember from a biology class somewhere in your life. So some of this stuff might be familiar, and maybe more familiar to you than to me, because I'm not a biologist or an optometrist, but this is my best understanding of what we're doing here, because then from here to astronomy, it's going to be a quick transition to get from one to the other. So our eyes take in light, focuses it with our lens onto the back of our retina. The back of our eye is called our retina, and we have special cells on the back of our retina that are sensitive to light. And remember, we have rods and cones. And which ones do we see color with? Cones. Cones for, yeah, C, cones color. We remember that part. I remember that part from high school biology. And we actually have 3 kinds of cones that are different from one another. So we have red, green, and blue. So the red cones specifically are sensitive to red light. And by that I mean, take the rainbow, cut it into 3 big chunks, and the reddish chunk is that whole amount of colors, so also orange, also some yellow, is what the red cones are sensitive to. And so when they look at the world with your eyeballs, they're looking in a black and white way, in the sense of like, is it bright or is it dim? And only in terms of red. So your red cones are making an image in your brain where it's bright, which we've been using white to represent for all things that are bright and red. So that guy, his name is Red Butler. Get it? Okay. He would appear very bright to the red cones in our eyes, right? Whereas I think his name is Buddy Blue, but now I don't remember, is going to appear very dark. If that's all you had, you wouldn't have much to go on. But you're really taking multiple images at once. So then your green cones, what are they going to see? Everything that's bright in green will be bright. Notice that the yellow color kid is like a little bright in both, because yellow is kind of in between. And so there's some sensitivity with both cones, right? And then blue is going to see the world in blue. And so blue things are going to be bright, like the background of that picture, and the blue and the kind of purplish indigo kind of kids. So then what your brain does is combine all 3 of these pictures, right? Something that is only bright to the red receptors is probably red. And something that is bright to maybe a couple of them, like the red and the green, we can figure out that that means yellow. So forms of color blindness are problems with distinguishing those or combining them in the ways that we would like typically expect, right? That's what your brain is doing, and you don't think about it, right? It just happens. But if you have the 3 types of cones functioning in the way we think that they should, then you're going to see the world in color in this way. So then, how do you do that with a telescope? We know that there's plenty of objects out there that have beautiful colors in space, right? So the telescope is going to serve like your lens, allowing the light through. And rather than your retina, you have usually a digital camera chip. So maybe a fancy one designed for astronomy, or maybe just like the one in your phone, right? And what you need to do, many of you are familiar with this and have done this plenty with the SLAS telescopes, I'm sure, you really need to take 3 different pictures. So you take all the light that's coming in, which is all mixed up, red, green, blue, everything in between, but you put a red filter in front of your camera so only the red light comes in. And that's like looking at the world with only your red cones if you could. I don't recommend trying to somehow do that. But it's artificially how we would do that. Then you take another picture, change your filter, change it to green, for example, take a green picture. Change your filter to blue, take a blue picture. There's other filters you could use, but these are like the most basic three and that match kind of what our eyes are doing. So then you have three different pictures. You need a brain to combine them, right? It's the computer. The computer is going to take those three images and combine them. I'll show you a more illustrated example of what that looks like in a little bit. But that's the basic idea. At this point, though, I do want to talk about why or how seeing things with your eyes or your smartphone camera is going to be different than the way that we see the universe with the James Webb Space Telescope, the Hubble Space Telescope, or any other like big astronomical telescope. The first key difference is something called aperture size. So an aperture is an opening. The opening in your eye is your pupil. And we can change that size a little bit to some extent. If you're in a very, very dim environment, then your pupils are going to be as big as possible to let in as much light. Then when you turn on the light, they will immediately close, right? And get a lot smaller because they don't want to let in so much light. It's too much. Even with as big as your pupils can be when you stand in the dark for like half an hour, they're still not very big compared to a space telescope, right? And so a telescope, the point of having a large telescope is to let in more light so we can see dimmer things. Another difference is something called integration time. So integration means adding up. So your eyes are going to take in a certain amount of light for a very split-second amount of time, and your brain's going to process it. And then it's going to take a new image and process it again, right? It keeps like looking at the world anew very quickly, faster than you can think about it. But with astronomical tools, we could just basically like keep getting more light and keep adding it up and not continually refreshing and making a new picture. We can even take multiple pictures and literally add them together because we have the memory of them saved on the hard drive. So we can also observe very, very dim things by just taking more time, getting more light in a big area and adding up that light over time. Another big difference is precision and calibration. If I'm going to use my phone to take a picture of my family to have a nice memory, I want it to look good, but I don't really need the numbers inside the computer or my phone to really be scientifically meaningful in terms of like how bright one part of the image is versus another. Whereas in astronomy, I'm really using these numbers to do math and to do science. And so I need to know if one part of the image, the numbers are twice as big as the other part of the image, that it's actually twice as bright. So I need to make sure that my instruments are properly calibrated and that they're precise, which means that I can trust kind of like when it says a number of 100, it's not like, well, maybe between 90 and 110. I need to know it's 100.01 or whatever, right? That's precision. We're not as worried about that with our phones. And then the other thing we can do with telescopes, which will really be what makes the images I showed you, and that we'll talk about more, what makes those images pop, is that we have access to the full electromagnetic spectrum. So the electromagnetic spectrum, by that I just mean light. And so our eyes can see a very, very small portion of the electromagnetic spectrum, the part that's a little rainbow there. And those are different wavelengths of light. But at longer wavelengths, we have infrared and radio. Microwaves are kind of like stuck in there. And then at shorter wavelengths, ultraviolet, X-rays, gamma rays. Objects in space are putting these out. Well, objects on Earth are also putting these out, but I'm more interested in the space stuff. And our eyes can't see them, but we have other instruments that can. And to give you an idea, when I say wavelength, like how big are these waves of light that we're talking about, this is kind of a visual that shows you, when I'm talking radio waves, I could hold one here in my hand, or even bigger than that, bigger than the size of a football field. Visible light is more like the size of a bacteria, and then we get into the smallest things we can possibly imagine, and maybe smaller than that. So we have telescopes. This picture shows you the ones that are like on Earth and the ones that are in space, not to scale, but along the whole range of the electromagnetic spectrum. Okay, so let's go back to one of the star clusters that I showed you on the title slide. It is this cluster this time. Here's a nice picture of it. And you might say, this is not one of the pretty pictures you showed me. That's fair, but also every astronomy picture is a pretty picture, so how dare you? But for real, this is a picture from the Sloan Digital Sky Survey. This picture is in visible light, so the kind of light that we can see. The Sloan Digital Sky Survey has what we call broadband filters. So in the same way that our eyes, like our cones, are sensitive to kind of like big chunks of light, big chunks of the rainbow, there are filters here that are sensitive to big chunks. They're not exactly red, green, and blue, but like kind of close. So this is the closest thing I can show you to a picture that's much like the process I just described, red, green, and blue, add them all together. We see that in this particular star cluster, things are pretty blue. There's a lot more blue here than red when we added it all up together. This star cluster is in the Small Magellanic Cloud. The Magellanic Clouds are like little tiny galaxies that orbit our galaxy. They are actually visible with your eyes if you're in the southern hemisphere in a very, very dark area. It's not something you can see here, so if you ever get the chance to go to the southern hemisphere, try to see those if you can. But this is a region where there are newly forming stars, and so that's very interesting for astronomers to study the processes of star formation. And that's why we see a lot of blue here, because some of those stars are brighter in the blue colors of the rainbow than in the red. Okay, so you're like, this is not a very pretty picture. Show me a pretty picture. I got you. Roughly lined up, as best I could in PowerPoint with this, is one of those beautiful new pictures from the James Webb Space Telescope. Huge difference, right, between these two. Let's take a moment to appreciate why there is such a difference, why there is such more artistic quality, you might say, to this picture than the one that I just showed you. Well, first of all, this one, all the stars that look like blobs, right? They're total blobs. The Sloan Digital Sky Survey is taking images from the ground within our atmosphere. So you're limited how fine of a picture you can get just from the atmosphere kind of messing everything up. And also you're limited by the size of the telescope. So this is very high resolution. One big advantage, two big advantages of the James Webb Space Telescope. It's huge, it's very big, and it's in space. So it doesn't even have to worry about the atmosphere. Now, another thing that adds to the richness of the color of this picture, on the right, I show you the different filters, in other words, the different images that went into producing this. And there are 9, did I count that right? There are 9 different pictures that are actually being combined to make this. And each of those pictures was assigned a slightly different color. They are color-coded here. So there's a few that are blue. I don't know if they put them in as the exact same kind of blue or what, but basically, a few that are blue, one that's like a cyan, green, yellow, orange, and then 2 that are red. One is maybe red-orange. But something you'll notice is that the James Webb Space Telescope is looking in the infrared. This is a picture of space that we cannot see with our eyes. And so that's another reason why this picture looks so different than the last one. The last one, that part around the edges is just dark. You can't see anything. That region is what we call dust. There's cold gas that's cold enough that the particles can kind of clump together a little bit, and so visible light can't pass through. But in the infrared, it's very bright and detailed. Another thing that adds to the richness and the artistic quality of this picture is that these filters are not broadband filters taking in a ton of light and everything that's going on in them. They're looking at really, really specific wavelengths of light. That symbol, looks like a funny U, is a Greek mu, and these are microns, or 1/1,000,000th of a meter, okay? So these are the different wavelengths. They're all around 1/1,000,000th to 4/1,000,000ths of a meter. But there's a lot of different stuff going on. When I look at this, I see a lot of orange and yellow around that outside part. And that's because the creators of this image made an artistic choice to represent those wavelengths. One of them says silicate. It's specifically that type of molecule that's creating that emission. And in the yellow, one is labeled PAH. That stands for polycyclic aromatic hydrocarbon, which is a fairly complex molecule as far as an astronomer is concerned, not as far as like a biologist is concerned. As far as an astronomer is concerned, a molecule like that that's very complex can only exist in cold places. If there's too much energy, if it's being bombarded with a lot of strong radiation, you're not going to have a molecule like that. It's going to break apart. And so by looking at this really specific wavelength of light, you're highlighting where PAHs can exist. So it's pretty, but there's also a lot of scientific detail here into the fact that we have these cold clouds of gas enveloping this kind of new star formation region. But then the picture that I actually showed you earlier is not this picture. It's this picture, which again, I tried to align using PowerPoint skills, and that may or may not have worked. This picture, take a moment to see the differences. It's the same region of space, but it has a very different artistic quality to it, right? And in this case, they use orange, yellow, green, and blue to represent, again, some of those infrared bands from the James Webb Space Telescope. But the red is from an X-ray telescope. That's a completely different type of energy on the electromagnetic spectrum. And particularly, those are highlighting young, massive stars that are putting out a lot of X-rays. And what I think is interesting about that artistic choice is that X-rays are high energy. They'd be closer to blue in terms of, in the visible light, if we want to choose colors to represent things, blue is higher energy, is closer to X-ray than red is. But they made an artistic choice to use X-rays as red, even though that doesn't really match, like, make high energy things blue. But this creates that kind of image. You could choose blue. You would be representing scientifically the same thing, but it would look really different, right? And that was an artistic choice that they made. I'll maybe just kind of run through this part really quick. This is the Lagoon Nebula. This is something that I actually have my students do. So this is one of the sets of images that I'm pretty sure you can get on JS9-4L if you wanted to play with it. It has 3 different images. These are from Hubble. These are visible light. And again, they're a narrow band that focuses on one specific kind of atom, not just everything going on in the red, but like really specifically what's going on. 502 nanometers to our eyes would be like green. And then 656 and 658 nanometers to our eyes would be red. But if you want to make a 3-color image like this, you need to have red, green, and blue at minimum. And then we saw you can also add in a ton of other stuff if you want to, add some complexity. But suffice to say, if you choose red, green, and blue, what you do is you take each of these images. Again, you can represent them as black and white because it's just dark or bright. But then where it gets interesting is when you color each one, pick one to be blue, one to be green, one to be red, you add them all up. If you just use the default values, it'll look like this, and you're like, this kind of is the color of sick, I don't know. So it's not a pretty picture if you use the defaults, right? You need to do that play, do that color scaling, choose a different scale, choose a different minimum, choose a different maximum, maybe emphasize different parts of the images than others to make an image that looks really nice, right? Oh yeah, I don't know if the video will work. That'd be great. I forgot I made that. Here's an example of like how you do that. Here's the green picture. And what I'm doing is changing some of the scaling, the brightness limit, the stretch, so that the whole image doesn't have like green everywhere. The green is concentrated in that middle part. So then when I add it all together, again, we got rid of that like green everywhere. Now I specifically look at the one that I chose to assign to red. Change that one a bit. I lowered that brightness limit, so all the bright stuff just is red uniformly, and then changed it to a different scaling. Now again, I have more of a bluish background, and the red is not so prominent. When I have my students do this, they come up with all different kinds of images, right? These are the same 3 pictures from Hubble. They have the same scientific content to them, but depending on the choices you make and how you represent the images, you get a very different expression of the cosmos, right? You can play with how you view the Lagoon Nebula, right? Is it kind of a scary Halloween-y thing? Is it like a vast ocean? Is it, some of these like pink ones make me think of some kind of like Valentine's heart thing, I don't know. So at this point, to kind of wrap it up, you might ask, all right, when you see an astronomy picture, is this how it would look to our eyes? I think you can confidently say, no, it is not. Probably because it may have different wavelengths that our eyes can't even see. Also, it's collecting more light than our eyes could possibly see, and it's combining things in different ways than our eyes do, right? Our brain just does it one way. Many of you have maybe experienced this when you look into a telescope, where you're like, wait, that's it? Like, sometimes that happens, right? But that's the power of taking these images. The next question might be, is it all just false color? Are these images all lies? To which I will say, no, it's not false color, but rather it is representative color. So remember, false color was when you just like assign colors to whatever and it makes no sense, like that weird rainbow picture I showed you of my dog, right? In this case, the colors are meant to represent something physically, and it might be very detailed, like the location and the brightness of polycyclic aromatic hydrocarbons is being represented by yellow. That's what we mean by representational color. So even though they're beautiful and amazing, right, there's truth behind them, is what I'm going to say about that. So after this, how will you play with art and science? I have a couple suggestions. You can, as I showed you, make your own astronomy art with JS94L, or maybe go the next level, get like telescope trained with the SLAS telescopes, take your own images, do some real detailed processing, if you want to get into that. Another cool tool that I used for that star cluster is Worldwide Telescope. This is a very cool tool. There's like guided tours of things. You can look up something if you're like, I heard about a cool astronomy object, I want to check it out. What's really nice about it is you can maybe zoom in on a particular object and then look at it in different wavelengths. You can look at different pictures from professional astronomers, from NASA, from ESA, from all these places, and see how things change when you look in different wavelengths, like we did with that star cluster. That's a really fun way to play with how you're viewing the universe and see all these artistic ways to understand it. Okay, and with that, I'll wrap up. Thank you.